Hello everyone, I'm Akash. In today's video, we will discuss a true-false question on topology. I have posted this question on our YouTube channel community post on 17th of April. The statement is, every interior point of a set S is also a limit point of S. We need to examine whether this statement is true or false. So let's begin the video. Let X be any set and tau be a power set of X. Okay, that is tau is discrete topology on X. Okay, topology consisting of all subsets of set X. Okay, so X tau is a topological space, and we consider let S be any non-empty subset of X. Okay, we have considered X tau be a discrete space, discrete topological space, and S be any non-empty subset of X. Since S is a non-empty subset of X, so this implies there must exist some A belongs to S. Okay, so this implies as A belongs to S, so set containing A subset of S, and hence it is consequently subset of X also, because S subset of X and set containing A subset of S, so set containing A subset of X also. So from here, and by definition of interior point of a set, we can see that A is an interior point of S. Why? Because what is the definition of interior point? A point A is an interior point of a set S if A belongs to S, if A belongs to S, and there exists a neighborhood of A which is contained in S. There exists a neighborhood of A which is contained in S. Here the neighborhood, that is an open set which is contained in S and containing a point A, is set containing A. Why this is an open set? Because it belongs to the P of X, and we call every set of P of X topology tau an open set. Okay, we call every member of tau open set, as this is a subset of S, consequently subset of X. So set containing A belongs to tau, and hence it is an open set. So there exists an open set which contains a point A and which is contained in S. So this implies A is an interior point of S. Now we will show that A is not a limit point of S. To see this clearly, there exists an open set that contains A and does not contains any point of A, any point of S distinct from A itself. Okay, by definition of limit point, we know that a point A is said to be limit point of set S if every neighborhood of A, hence consequently every open set containing A, contains at least one point of S distinct from distinct from A itself. But clearly here there exists an open set that contains a point A but does not contain a point of S distinct from A itself, and that open set is set containing A, namely set containing A. Because this is an open set, because this belongs to tau, so this is an open set and it contains point A and does not contains any point of S distinct from A itself. So there exists a neighborhood of A which does not contains a point of S distinct from A itself. So A is not limit point. So this implies A is not a limit point of S. So in this case, we see that the given statement is false. Here we have taken the point A, which is an interior point of set S, and clearly here we have seen that A is not a limit point of S. So the given statement is false. However, if it is given that S subset of Euclidean space with usual topology, then the given statement will become true. Okay. Here it is not given that, that's why the given statement is false. But if it is given that S subset of Euclidean space with usual topology, then this statement will become true. To say this, let X equals to R with respect to usual topology. Okay. And let S subset of R, okay, and let P be any interior point of S. Okay, we have taken S subset of X equals to R. Okay, so S subset of R, and let P be any interior point of S. By definition of interior point, P belongs to S and there exists a neighborhood of P which is contained in S. Okay, there exists some neighborhood of P which is contained in S, and we know that neighborhood in case of real numbers are open intervals. Okay, this is an epsilon neighborhood of P minus epsilon comma P plus epsilon. Okay, in case of real numbers, neighborhoods are open intervals. So as there exists some neighborhood of P which is contained in S, so this implies there exists open interval AB such that P belongs to open interval AB and which is contained in S. Okay. Now, from here we can see that as P belongs to this open interval, so every neighborhood of P contains at least one point of this open interval which is distinct from P itself. No matter how small we take a neighborhood, there exists some point of this open interval which is distinct from P itself. Okay. So every neighborhood of P contains at least one point of this open interval which is distinct from P itself. Hence, consequently, at least one point of S which is distinct from P itself. And that implies P is a limit point of S. Okay. Thus, we see that if we take X equals to R with a usual topology, in fact, if we take X equals to Rn, n-dimensional Euclidean space with a usual topology, then the given statement is true. Okay. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.